We talked about joint PDFs for random vectors of size 2, of dimension 2. Of course, that is generalizable. And for a general random vector of size n or dimension n, the joint PDF is the n-fold derivative of the joint CDF, and each of these derivations, differentiations, are with respect to each of these different parameters, x1 through xn. Okay, and of course we have the other the relationship in the other order. The CDF, the joint CDF, can be written in terms of the integration of the joint PDF, where you integrate the joint PDF with respect to each of the parameters, um, t1 through tn, from minus infinity to x sub I, let's say. Okay, x1, x2, xn, etc. And of course, the joint PDF also, as with the PMF, as with the CDF, it satisfies the conditions, the properties of the general PDF. Okay, remember the PDF is a non-negative function and the area under it is 1. Now the area, of course, will be a generic term here because we are talking about higher dimensions. So for instance, well, a two-dimensional integration will give you a volume, etc. So the volume under this hypersurface, let's say, should add up to 1. And of course, for any parameter you provide to the joint PDF, the value should be non-negative. Okay, so these two are important generic properties of joint PDFs. Now, when you have the joint PDF, of course, that gives you all behavior you need. Now, from joint PDFs, you can go to joint CDFs. From joint CDFs, you can go to joint PDFs. Maybe one point I should make here is, well, we will talk about marginal PDFs in a minute. In fact, let me show you that. And this holds for also PMF, CDF, and PDF. When you know the joint distribution, either in the form of a PMF or a CDF or a PDF, you can go to the marginals, right? We have mechanisms for that. And because you know the joint behavior of the random variables, each of the components, you can extract the general behavior of one of them or a number of them, as a subset of them. But the reverse is not true. For instance, if you know the marginal distribution of x1 and the marginal distribution of x2, you cannot directly write the joint distribution. This is a very important point, okay? This is confused a lot of times. If you know the marginals, in general, you cannot go to the joint behavior because that's more information. When you have the marginals do not have information regarding the other components. For if you have the marginal PDF of x1, let's say, that distribution has no information on how x1 interacts with x2. Okay, that's important. If you have the marginal distribution of x2, that distribution has no information on how x2 interacts with x1 or how x2 is affected by x1. When you have the marginal, when you have the joint distribution, that information is readily available in the joint distribution. You have all the information you need in the joint distribution. That is the entire picture, as good as it gets. But well, from that you can go to the marginals, but that procedure loses some information. Okay, so from joint distributions you can go to marginals, but from marginals you cannot always go to the joints. Okay, so let's see how we can obtain marginal PDFs from joint PDFs. Recall for CDFs, if you evaluate or if you take the limit as x2 goes to infinity, you get the marginal CDF of x1. Or if you take x1 to infinity, you get the marginal CDF of x2. Now, let's say I would like to obtain the marginal PDF of x1. But by definition, that is the um, derivative with respect to x1 of this. the marginal CDF of x1, but that is equal to this, right? The joint CDF evaluated x1 and infinity. And I can write this as an integral. Well, x1, t1 goes from minus infinity to x1, and x2 goes from minus infinity to infinity, because this is infinity, right? When you differentiate this expression, this double integral, with respect to x1, right, by the fundamental theorem of calculus, you just get what is inside this, evaluated at x1 for t1. So whatever, wherever you see t1, this here, you insert x1, and that is the result of the differentiation. So this is what you get. So you see, to obtain the marginal PDF of x1, what you do is you integrate the joint PDF over the entire real line with respect to the other component, x2. You see, this resembles the mechanism how to find the marginal PMF from the joint PMF, because that was a summation over the entire sample space of the remaining components. So this is the same thing. So for instance, to obtain the marginal PDF of x2, you integrate the joint PDF with respect to x1 over the entire real line.